You can do Gaussian elimination, substitution, whatever you're more comfortable with. I just happen to like matrix inversion, but you don't have to do that. And then did I hear a yes for the yeah, okay. All right, well, let's take a look at
Substitution.
Okay, so when you have a matrix, I call this matrix A, and then I'll step backwards and we'll look a little bit at the algebra here just to make sure that everybody's comfortable with that. And also, like I said, there's other methods. You don't have to use this for solving linear equations. But the way I like to do it is I take the matrix, and remember the first thing you do is to find your submatrix determinants. So that means that for this submatrix, I cross this out, I cross that out, and it's 0 times 0 minus 0 times -5, or 0.5, that's 0. For another submatrix determinant, so first of all, you find the determinants for all the submatrices. That's 9 of them. And remember what you do to find submatrix. Let's just arbitrarily, since this has a value, -0.8, you cross out the column, you cross out the row. It's 1 times 0 minus 0.8 times 1, so that's -0.8 for that. Does it sound familiar?
Yeah.
Okay, so the next thing you do is, so that's all, you do that 9 times for all submatrices. Then, the way I do it, because I do it in Excel, is I have all the cofactor signs. But remember, the cofactor is -1 to the I plus j, where I is the element row and j is the element column. So the pattern that it ends up with, this is -1 squared, so it's +1. This is -1 to the third because it's row 1, column 2. This is row 1, column 3, so it's -1 to the fourth, and you end up with this kind of a pattern. Right? So then the cofactors, the cofactor of A is the cofactor sign times each of the submatrix determinants. So that becomes 0, 0.5, 0, 0, 0.5, -1 times -8, 1 times 0.4 is 0.4, -1 times 1 is -1, and 1 times -8 is 0.8. That making sense. I kind of divided this into 2 steps just because I was doing it in Excel. But remember, what you're doing is
You're applying the cofactor to the submatrix.
That's right. Yeah, that's right. That's what you're doing. It's a cofactor to the submatrix. -1, the I plus j times the submatrix. And I'll just call it A, B, C, D. And you do that for every one of the every one of your submatrices, every one of your elements. So you have to do that operation 9 times in 3 by 3. The determinant of the matrix A then, remember, is I'm just looking at what I did here. And you can take any row or column. I happen to have taken A, which is the element of A times submatrix times the cofactor, and then you add it to the next element times its cofactor, and the next element times its cofactor. So in this case, I did I did the first row. But remember, you can use any row or column, and the determinant is the same. Does that ring a bell? Kyle?
Yeah, do you remember what I guess class the slides I could look at to refer to that?
Yeah, this was in QM in topic 5, the regression. So then the cofactor is just the submatrix times the cofactors. Then the adjoint is just the transpose of the cofactor. So this row becomes this column, this row becomes this column, this row becomes this column. And then to invert it, we take the determinant times each one of the elements of the adjoint. And that's the inverse of the matrix. And if you misplaced or gleefully destroyed the QM notes, just send me a note now, and I'll send it out again to you. I'm going to have to do matrices when I do this from now on because I won't be teaching QM anymore. So I'll insert that in here.
The inverse, to get from the adjoint to the inverse again, that was...
is the determinant times each element of the adjoint.
Okay.
Not divide, the determinant, each element divided by the determinant, not multiplied by. Each element divided by the determinant. I knew it didn't sound quite right now. Didn't realize what I said wrong. Anyway, then once you've got that inverse, then you can take that and multiply it by B, which is your F matrix. In this case, it's the value matrix, associated in this case with the value associated with never fertilizing 5.3 and 3 and -1. And the inverse, so that's a 3 by 3 times a 3 by 1 gives you a 3 by 1, and this is X. Remember, if we eliminate, if we just set F3 equals 0, this is always the value of E, the value of F1, and the value of F2 in this matrix. Now, once we've gotten those solutions, then you can go back to your value determination, your policy improvement step, because now we've got the 12.88 here for the F matrix and 8 and 0. And we have, and this is more similar to the finite analysis after this point, where you just take the value associated with never fertilizing, transition matrix associated with never fertilizing, and current F matrix, F value matrix. And that's where we get this, and we substitute in for K equal 1, for never fertilizing. Then you have to go back and do your second, and do the K2, where now we put in the value associated with always fertilizing, transition matrix associated with always fertilizing, and our 12.888 that we got from our simultaneous linear equations. And now we have the value associated with always fertilizing, and then we can do the optimal solution step. That's the end of the step. So the solution is always to fertilize for that step. Now we have to do it at least one more time to make sure that it converges to the same solution. Now we set our evaluation equal to, in this case, V2, which is the always fertilized value, plus P superscript 2, which is the transition matrix for always fertilizing, our F, which we don't know at this point. We don't know what the F matrix looks like, minus the F matrix. And those are our unknowns. We've got 3 unknowns, and then we have the E, which is still unknown. We expand those just by matrix, the usual matrix methods. Expand those out to this, and you set F3 equal to 0, and you isolate the 4.7, 3.1, 0.4 on one side of the matrix, because that's your V matrix with solution. And your 3 unknowns, E, F1, and F2, are now in the body of the linear equations. Now that 1.7 and -0.6 is what I called the A matrix that I inverted and found the determinant, and et cetera, et cetera. And this is what I called the B matrix, which then I multiplied by the inverted matrix. And in this case, the E came out to 2.26, the F1 came out to 6.75, and F2 came out to 3.79. Let's go look at the spreadsheet just to prove that to ourselves. And this is for iteration 2, and the only fertilization policy. This is our A matrix, and through the whole thing again. This is the inverse, and this is what I arbitrarily called B, which is really the value matrix. And this is then our values for E, F1, and F2. F3 we've arbitrarily set to 0, exactly. So now we're ready to do the policy improvement steps with always fertilizing, and that's what our value is for never fertilizing. Our policy improvement step for always fertilizing, and now we can do the optimum, which is again always fertilizing is optimum. So that means that for the long run, it's converged now to the same solution twice. We can stop. So for the long run, we always want to fertilize regardless of the state. Maintain a good garden makes sense. Is everybody comfortable with not only the idea, well, let me put it this way. Are you comfortable both with the manipulations, the arithmetic of it, as well as the interpretation of it? And remember, the first step, the first type that we did was the finite stage, where you say, okay, I'm only interested 3 years, I'm only interested for 4 time units, whatever. And then you start at the end with your last time unit and work backwards. And so that means that in this case we did 3 years. That was our time unit. We start with 3, and 3 is simple. We take our value matrices for never fertilizing, always fertilizing, and figure out what the best is. That's what we do in the last stage. Then we work backwards to stage 2, and evaluate it for never fertilize, evaluate it for always fertilize, and then we get a result. And we end up in stage 1, never fertilize, always fertilize, result. And you are welcome to look anywhere for, solving simultaneous linear equations. You can look in any math book and figure out what works best for you. And just kind of matrix thinker, so that works better for me. If you, like I said, if you want how I worked out these examples in the lecture, if you would like the spreadsheets, send me an email. I'll make a version of it that I'll send out. Most of it's just my notes you won't be interested in anyway. It's just things that I made to put a copy of the lecture. But if you want those pages out of that spreadsheet, just let me know. I'll make a version of it. Also, if you want the QM matrix analysis or matrix arithmetic section, I'll send you that whole thing as well. But just, I'll wait for you to ask for it. I won't send it out. So having said that, is everybody comfortable moving on to the last topic, the hazard analysis?
Yeah. Is there a problem comparable to this in a one way?
Yes.
Okay.
Yes, there is. There's a problem comparable to both of these.
Okay.
And then another one in the practice problem set. So there should be a good supply of practice. Okay, final topic. I have picked out some hazard analysis techniques that you will be doing what I don't do. You're doing the leftovers for your paper, what I just opted not to do. Most system, or many, I won't say most, but many system safety classes spend a great deal more time on these than I do. I frankly don't think they're complex enough to warrant that much time. So that's why I try to give you a lot of other operations research and systems analysis, or yeah, operations research techniques, systems analysis techniques, and other things that I think are relevant to system safety and the practice of safety in the workplace in general. So that's why I compress what I do about these analysis techniques. So, like I said, simply because I don't think they're complex enough to warrant a lot of time, more than a couple of weeks on them. A bunch of topics, or a bunch of references for your use. The hazard analysis, we go back to the first day that we talked, sort of falls in this section. There's a staggering number of names of analytical tools that are out there. The System Safety Handbook that I have, it's that there's probably at least 100 of them that have been named. The trouble with them, I think, is that there are, at least for every name, I mean for every, well, let me put it this way. If we group them by similarity, they would probably reduce to about a dozen, because so many of them are just slight variants on the other ones. I mean, the only one that's truly distinctive is fault tree analysis. All the rest of them, the FMEA, the FMECA, and some of the other techniques that I've listed here, are virtually the same thing. They just have, like I said, they have slight variants. They are what's called inductive, and we'll talk about that in a minute. And most of them really are just a systematic way to brainstorm about what can go wrong, just like FMEA is. So I have opted to do the ones that I think are the archetypal ones for each one of the techniques. And like I said, I think fault tree is truly distinctive. Inductive versus deductive. These are logic terms that pretty much apply here. Inductive is bottom up. And what you do with inductive techniques is you sit down and you enumerate everything that can go wrong, essentially. And it's just like inductive logic, because that's what inductive logic is. By enumeration, once I get to a certain point, I believe that I have proven something. And the trouble with inductive logic is that one case can disprove it. and the famous biological instance of swans. I don't know if you guys are familiar with that, but for many, many years, they believed that all swans were white, biologists, ornithologists. And that was a defining characteristic of that species. Or it might be more than a species, it might be a genus or something like that. But anyway, that's how they classified them, based on color, among other things. And then suddenly, they found that in Australia, I believe, when they fully explored the continent, they found black swans. And that just obliterated all the inductive logic about swans being white, because all the ones that they had seen up until that point, all the ones the biologists had seen were white. And it turned out that not all swans are white, there are black swans. And that's one of the problems with inductive logic, is that just because you can't think of something happening doesn't mean that it's not going to. Okay? But nevertheless, that is a very, very common approach that's used. And I'll bet a good 3/4 of the techniques in the System Safety Analysis Handbook are inductive in nature of one type or another. Because that's something you can do. You can get together in a room and everybody can talk about it. And that's what we like to do. You know, that's what we do best, is we talk about it, and we write everything down, and we do the best we can. So a lot of techniques are inductive in nature. The ones that I think are better are deductive. And in logic, deduction is a syllogism. I always forget a good syllogism. I try to come up with these myself, and I end up with something pathetic. So let's do a syllogism here. So I can show you a good syllogism, and it usually isn't a good one. Okay. So let's just do not very imaginative. And you will know what definitions in this. Too much detail here. Here they probably have one. You have a general argument, all men are mortal, and we know that John is a man, and therefore John is mortal. Nothing profound about it, but that is the standard format for a syllogism. You start with a premise or an argument, and then you end up with a categorization and a conclusion. And that's classic deduction in logic, is the use of a syllogism. Well, the way that that's applied in these system safety techniques is what we call top-down. You start with the outcome, the failure, and then you work backwards to figure out what the contributing factors for that failure are. And if you're lucky, you can get some probabilities associated with it and use Boolean logic. So it is more deductive in nature because we started out with an argument. This failed. What were the contributing elements of that failure? This is usually the. I'll say that this is usually the approach used in root cause analysis. However, root cause analysis is really a more eclectic approach. They sometimes use fault tree type approaches in root cause, but then they also use Ishikawa diagrams. They use a variety of approaches, the 5 whys. It's a way to use an eclectic gathering of techniques in order to get to the root causes. And it really should be called root causes because it's often criticized for trying to find one cause when that's not realistic in most circumstances. There's usually multiple causes to most things. So we can generally classify our approaches as inductive or deductive. Fault tree analysis is the classic deductive. FMEA is the classic inductive. Okay, and that's why we'll talk about those two first. Okay, so let's talk about fault tree first. It is deductive because we start with the outcome. So what is the failure that we want to analyze? It's top down rather than bottom up, and saying, okay, what are all the things that can go wrong, and then what do we do about each one of them? Here we end up with a specific failure, and we do an analysis of it. It's graphical. It has a lot of, as I'll show you, that it has a lot of symbology associated with it, with standard and fault tree diagrams. It can be qualitative or quantitative. It's better if it's quantitative, but since you don't always have quantitative data on failure probabilities, on reliability, which you often do and sometimes you don't, you can look at it from a qualitative perspective, and that's fine, because qualitative allows you to, without getting an idea of the probability associated with the outcome, you can get an idea of what contributes to the outcome, and approach it that way. And then finally, and this is actually true of all the techniques we'll be talking about, it's a systematic approach. Even if we're just enumerating, if we systematically enumerate by subsystem, for instance, and then try to determine how to ameliorate each of the failures, when it will fail, and how to ameliorate it, that's a systematic approach too. So that's kind of, even though it's often applied to fault trees, it's true of all the techniques we'll be looking at.
I find the word systematic is kind of thrown around a lot. Like a systematic approach sounds better than an approach.
Yeah.
In industry. So in this case, a systematic approach truly means breaking it down
into systems.
Into systems.
Yeah, yeah. Generally, systematic is used as a methodical approach rather than truly a systematic. And in this one, yeah, we try to break it down into subsystems and analyze it by subsystem, and then put them together for your final product. Okay, so let's look at some of the symbols. The rectangle is our top-level event, our top-level fault. It can be an intermediate or terminal event. In other words, at the top of the tree, but it can never be an initial event. The initial event is at the bottom of the tree. Usually, you will see, you have to see this at the top, because the first thing you do with systems, with a fault tree analysis, is to determine what outcome you want to, or what failure you want to analyze. So that has to be at the top. Whereas the initial events, which is the basic event, which is the circle, is what you see at the bottom of the tree. Those are the things that are the most basic element that we can imagine, and they go in circles at the bottom of the tree, because we can't analyze those any further. Now, if we choose not to analyze them, but we can, there's another symbol for that. These are the things that really can't be broken down any further. And this is where you assign your initial probabilities, usually, if you have them. This is what you do is you have an event and you say, yes, this is going to happen, and it contributes to other events, but I choose not to analyze it. It's not relevant for this analysis. That's the diamond, and the sideways diamond like this. And you can still, you can treat it with a probability. You can treat it like a basic event, but this indicates an awareness that it's not a basic event, which you're treating it like one. If you have an event which is normal and basic also, then it gets this little pentagon house kind of shape. Things like an on-off switch is often given this. This is a distinguishing kind of binary basic event. It has a probability of 0 or 1. It's on or off. So far, so good? The oval, and I'm just running through these so that you have an idea of what when we start talking about them, you have an idea of what they look like. This is a condition modifier. There's certain gates, certain types of trees that, or tree elements that are called gates that have a modifier or a conditional component to them. That conditional component is explicated inside of an oval, and then it's attached to the gate. The triangle is a transfer symbol. So this symbol, that means you couldn't get it all in one page and go to another. But it indicates to go somewhere else, and you can put a notation in there so that you know which other page to go to somehow. Like this is A, and then the next page you see A again. And I think I changed it on one of these, but I had one that I should have put a transfer symbol on. I hope I did. If not, we'll put them in later when we talk about it. Now, two types of gates, and OR gates. Both of them are Boolean in nature. Okay? The AND gate is this inverted U that's closed. That's like a Boolean intersection. And if you have probabilities for your basic events, and these aren't basic events, but these are things that probably shouldn't have happened. Now, I copied those out of bar, and they're not. That's the one thing that's a little irritating about about all of the references is that they define these symbols, but then they don't always conform to them. So even though he classified these as failures, power applied greater than 1 millisecond, 5 milliamps of current in the system, that's really a basic event, right? Because he's applied a probability to it. So, but I cut and pasted that out. So that's what, the way Barr drew it. I wouldn't draw it that way. Kind of thinking about it now, I probably ought to redraw that on my own. So anyway, this is an intersection. This is an AND gate. An AND gate means that for the fault to pass, both of these conditions have to be met. You have to have 5 milliamps of current in the system, and the power has to be applied for a time greater than 1 millisecond. And it's a Boolean AND. And a Boolean AND, as you know, is an intersection, right? So if E and F are independent, then the probability of D is E times F, or E intersect F, or E given F times the probability of F, or F given E times the probability of E, because you remember the result from Bayes theorem, right? And so, if they are not conditional, that means that the E times F is the same as E, or E given F is the same as E, and F given E is the same as F, because they don't intersect well. So that means that this will always reduce to E times F. So that means that I just take each one of those probabilities, and the probability of an overheated wire is simply the probability of E times the probability of F, and that is that very low probability of that fault occurring. And typically, if there are conditional, if there's a conditional basic event, we use another approach. We use a conditional gate of some kind, rather than trying to deal with it with conditional probabilities in our Boolean statement, or Boolean equation. This is an example of a modifier. Roland and Moriarty are much more meticulous about their use of symbols. That's why I like Moeller and Moriarty. I'm sorry that I print. Otherwise, I just signed up for the class. It's a really good book. But anyway, this is a conditional modifier. It's a priority AND gate. This means that if C happens first to R1 and R2, then the fault will pass. So C happens first before R1 and R2 happens, but all three of them have to happen for it to occur. So this is a priority AND gate. It specifies an order of occurrence for basic events for the fault to pass. So if R1 happens, and then C, then R2, then the fault won't pass. Now, the other basic gate is the OR gate. And see, this is again from Barr, and he has this inexplicable use of rectangles when it should be circles, but nevertheless. And this is the inverted U with the curved bottom. That's the OR gate. And it's a Boolean union. You add the probabilities. That means that if at least one basic event occurs, the fault will pass. Both of them don't have to occur. Any one of them occurring will allow the fault to pass. So if switch A is open, you'll get no current. Or if battery B has 0 volts, you'll get no current. If they happen together, it doesn't matter, because any one of them will occur. So again, you just add probabilities for B and C. B union C is, of course, B plus C times the intersection. But the intersection is 0 because they're not dependent on each other. They don't intersect, so it reduces to E plus C. So the probability of the fault passing is simply the probability of A plus the probability of B, or probability of B and C, I'm sorry. And just add them together. There is such a thing as an exclusive OR gate. See the modifier? It says exclusive. This is an OR gate. You just simply attach it by a line without an arrow. So it's an exclusive OR gate. If A occurs, the fault passes and B can occur. If B occurs, the fault passes and A can occur. So this is a shorthand. That means you can, if you wanted to, you could reduce, or what the term that they use is resolve it into a more complex tree, but one that's simpler to read. So this is an AND gate and an OR gate. An AND gate is A and not B. Fault will pass and E will pass. E will occur. Not A and B. Together, fault 2 will pass and E will occur. But both of these can occur. But if either one of them occurs, the fault will pass. So this is the resolution into simple AND and OR gates for this exclusive OR gate. Make sense? The next is a summation OR gate. This is probably the most complex one. Modifier is your model, whatever the model is. And in this case, I copied this one out because this is a really complex model where we have, and also remember that there has to be a summation sign inside the gate to indicate that it's a summation OR. So we have P sub I, T sub I, and A sub I as our basic events, and then the summation OR. Conditions for the fault to pass, and that's what you have to enumerate. If T sub I is greater than some value T, that in and of itself will allow the fault to pass. If P sub I is greater than or equal to some value P, then that is sufficient for the fault to pass. A sub I is greater than some event A, then that's sufficient for the fault to pass. If t sub 1 is between, if t sub I is between some value t sub 1 and t, and p sub 1, p sub I is between some value p1 and p, then the fault will pass. And you can see where this is going. This is a highly specific set of conditions for the fault to pass. So this is 1, 2, 3, 4, 5, 6, 7 sets of conditions that, when they occur, will allow the fault to pass. So this is pressure, temperature, and acidity conditions. That's what PT and A stand for, thermal and Moriarty. And that's when you have, like I said, a very specific set of conditions that you want to enumerate that will indicate that the fault will pass to the event E. Now, again, this can be resolved into simple and, so to speak, into and OR gates. So I have here an exclusive OR, which means that it has to be any one of these things occurring. That's not too complicated, exclusive. Okay, that I can deal with. But in it I have 1, 2, 3, these two conditions occurring together, 4, 5, 6, 7. So any one of those 7 things, those 7 models that we outlined in the previous slide, occurs, then fault will pass. And this is the second model, where t sub I is between some values, p sub I is between some values. Here t sub I is between values again, and a sub I is between some values. Those both occur. P between some values and A between some values that occur. And then all 3 of them between some specified values together will cause it to occur. So any one of those 7 conditions will allow the fault to pass. And an inhibit gate means that given a condition, the fault will pass. This is kind of a really simple version of a summation OR because we just have one condition. We could have done it with a summation OR with just one model, but this is easier, the inhibit gate. And the inhibit gate is the only one that has this hexagon indicator. That's if that event occurs, the fault will pass. And you have to know what the event is. The O-ring, an O-ring seal. If it fails below a certain temperature, then you're going to get a fault. Period. It's a very simple set of conditions. And that's the inhibit gate. M out of N OR gate or M out of N voting gate is another one. What that means is that if any set of 2 events occur, that the default will pass. Now, here we can, this is very shorthand for the resolution. Resolution here is, that means any set of 2. So 3 objects taken 2 at a time, that means I have 3 possible sets. So the 3 objects, so it's A1 and A2, or A1 and A3, or A2 and A3. And so these are AND gate and OR gate for one of those, any one of those 3 sets of 2. This is for your reference, because we'll be talking about because we'll be using some of the engineering notation simply because it's more, it's easier to use. It's easier to write that than the intersect and union signs are. The union, you use a plus, intersect, you use an asterisk. And it just shows you the relationship. And lots of times the asterisks are dropped so that you can just write it without even the asterisk. But you can't drop the plus signs for the union. And it's a lot simpler to use. and it shows you all the laws expressed in set theory and the union and intersect symbols, and expressed with the quote-unquote engineering notation. Like I said, I like the engineering, what he calls the engineering notation, just because it's a lot easier to write it. Okay. All right. I think that I'm going to wait till next time to get into the synthetic bulk trees. We have plenty of time. So I'll start out next week going over the problems for the decision analysis, and then I'll finish this topic, and that'll be our task for next week. Yeah, we've only got 40 slides to go, so we got plenty of time next week to do this. Rather not flood you with too much in one session. Any questions about what I've talked about so far, just the symbology?
We use brackets. We use that brackets for n, right?
These brackets?
Yeah.
Uh-huh.
Is this specific for n?
No. Well, actually, yes. In this case, we are using that one. Yes. Yeah. It's specific. That means that both of these have to occur, so that means that you can resolve it into an AND gate with an AND gate. Yes. Sorry, I didn't see you raising your hand. Anything else? Okay. I'm trying to rush you away. No? Okay. Well, I'll see you next week then.